Now that we've set up our project and linked the required files, it's time to launch ANSYS Fluent to begin the actual simulation setup. To do this, simply double-click on the setup cell in your Fluent system. This will open the Fluent Launcher window. Here, make the following selections. Choose 3D under the processing options, since we're working with a three-dimensional mesh of the parking garage. Enable double precision for higher numerical accuracy, especially helpful in fire and heat transfer simulations involving small gradients and multi-species models. If your system has multiple CPU cores and the proper parallel licenses, you can also enable Fluent Parallel to speed up the calculations, but for most users, the default serial setup works fine. Once those settings are in place, click Start to launch Fluent. Awesome! Now that Fluent is running, let's move on to the next important step, importing the mesh and getting it ready for simulation. Go to the File menu at the top of the Fluent window, then select Import Mesh. From the file browser, choose garage.msh, the mesh file we placed in the user_files directory earlier, and click OK. Once the mesh is loaded, it's always a good idea to check for any issues. Go to the console/TUI window and type or click Mesh. Check if everything is fine. Fluent will report that no errors were found. If there are any warnings, pay attention to them. Now we'll reorder the mesh to improve solver performance. Navigate to Mesh Reorder Domain. Why reorder? Because this process optimizes how nodes, faces, and cells are stored in memory, which can make your simulation run faster and more efficiently, especially in large-scale models like fire scenarios. Next, we'll enable gravity, since our simulation involves buoyancy-driven flows caused by hot rising gases. Go to the operating conditions, enable gravity, and set the gravitational acceleration to z equals -9.81 meters per square second. Remember, this step is essential in fire and heat transfer simulations, because it ensures that hot gases rise in cooler air sinks, just like in real-life fire events. No need to change the solver settings at this point, keep the defaults for now. Alright, we're making great progress. Let's move on to setting up the materials and species in the next step. Now let's move on to an essential part of any CFD simulation, turbulence modeling. To define how turbulence behaves in our simulation, in the navigation pane, click on Models. Then, double-click on Viscous to open the Viscous Model panel. Here's what to select: k-epsilon, 2 as the main model. Standard as the k-epsilon formulation. Enhanced wall treatment for the near wall treatment. Why did we choose these settings? The k-epsilon model is one of the most widely used turbulence models. It's known for being simple, robust, and computationally efficient, especially in fire and ventilation scenarios like this one. The standard k-epsilon formulation works well for general-purpose flows and is a solid choice for indoor environments with jet-like behavior, such as exhaust fans and smoke movement. We selected enhanced wall treatment because it improves accuracy near walls and solid boundaries. This is crucial in our simulation, where hot gases interact with ceilings, walls, and ventilation ducts, exactly where precise temperature and velocity profiles matter most. In fire-driven flows, turbulence plays a key role in mixing hot gases, oxygen, and smoke, so setting this up correctly is critical. Once these options are set, just click OK, and you're ready to move on. Alright, now it's time to define how thermal radiation will be handled in our simulation, which is especially important in fire scenarios where high temperatures play a major role. Here's what we do. In the Model Selection pane, double-click on Radiation to open the Radiation Model panel. In the list of available models, select Discrete Ordinates, DO, set flow iterations per radiation iteration to 1 and click OK. Why choose the Discrete Ordinates, DO, model? Because this model can handle both optically thick and optically thin media, making it perfect for realistic fire simulations involving hot combustion gases like CO₂ and H₂O, which absorb and emit thermal radiation. The DO model is extremely flexible. It covers surface-to-surface radiation participating media like combustion gases and works well in complex geometries, like our ventilated parking garage with a car fire. Once you click OK, Fluent may notify you that material properties or methods have changed. That's normal. It just means that the solver is preparing to calculate radiative heat transfer, and certain gas properties, like absorption coefficients, will be needed later. Also, note that when radiation is enabled, Fluent automatically activates the energy equation, since thermal modeling is now essential to the simulation. Great! With the turbulence and radiation models now set up, we're one step closer to a fully defined fire simulation. Now we're going to enable another key physics model in our fire simulation, species transport. This allows us to track different chemical species like nitrogen, oxygen, carbon dioxide, and water vapor as they move and mix throughout the parking garage. Here's what to do. In the model selection pane, double-click species to open the species model panel. From the available options, choose species transport, then click OK. But what does this model actually do? We're not simulating the combustion reaction itself in this analysis. Instead, we're modeling the products of combustion, meaning the hot gases like carbon dioxide and vapor that are already present in the environment as a result of the fire. By enabling species transport, Fluent allows us to track how these gases move with the flow, visualize their concentration, analyze their effect on temperature, density, and radiation. Just like when we enabled the radiation model, Fluent will now prompt you that new material properties need to be defined. Don't worry, click OK, and we'll take care of those settings later. Also note, the default mixture already includes nitrogen, oxygen, and water vapor. But we can later modify it to include carbon dioxide, which is crucial in a combustion scenario. So, by activating the species model, we're preparing our simulation to reflect realistic fire conditions with actual combustion gases, not just heat or air. That's it for part 2 of our fire simulation series in ANSYS Fluent. In this part, we successfully activated key models like radiation and species transport, and explained how they help us simulate realistic combustion gas behavior. Thank you so much for staying with me so far. If you're enjoying the content, make sure to like, comment, and subscribe so you're notified when the next part is out. See you in part 3.